welcome. We have been discussing about Krylov subspace. So, Krylov subspace as defined is a subspace generated by an n into n matrix A and a vector f in R n, which gives an m dimensional subspace which is spanned by all the vectors f, a f, a square f to the power up to a to the power m minus 1 f. What we have seen that if we can find out an update of Krylov subspace of A and the initial residual are 0, we can probably in single go we can update any guess solution x 0 to the solution of x is equal to b. Some hint like that we obtained from our last class's discussion. So, this subspace is called a Krylov subspace given after the name of Russian mathematician Krylov, and these vectors are near independent spanning vectors, because if f is not an eigenvalue of A and if f is also f is non-zero, f cannot be 0 here. If f is 0, then all the vectors are 0 and they are dependent, but if f is non-zero and f is not an eigenvector of A, then f and a f are independent. Similarly, I can say that f, a f and a square f will be independent if a f is not an eigenvector of a square f, and f a square f, a cube f will be independent. So, we can create a number of independent vectors and that will span the entire Krylov space up to the value m we are considering, but there will be a grade of this space that after that we cannot add any further a to the power m minus 1 f and say that these are independent. Once we have spanned the entire R n, we cannot add any further vector basically. So, this comes from Carey-Hamilton theorem. Carey-Hamilton theorem says that if polynomial of lambda or comes from the characteristics equation a minus lambda I. If p lambda is equal to 0, the characteristics equation can be written as p lambda is equal to 0, then p a is also equal to 0. That means that if I have determinant of a minus lambda I, this equation, this gives me something like a 1 lambda to the power lambda to the power m minus 1 plus b 1 lambda to the power m minus 2 plus, or I am sorry, a 1 lambda to the power m. So, this is m plus b 1 lambda to the power m minus 1 plus just one second, let us do this a 2 instead of a 1, this is a 2 plus a 2 lambda plus a 3 lambda to the power m minus 2, so on up to say 1 is 0 and m minus m. So, up to a m plus 1, something like this. Then if this is 0, Carey-Hamilton theorem says that this is the characteristics equation. Vector is that this equation will be utilized to find different roots of lambda and different eigenvalues. If this is the characteristics equation, then I can actually write a 1 a to the power m plus a 2 a to the power m minus 1 plus a 3 a to the power m minus 2 up to a m plus 1 is equal to 0. When doing this, if m is equal to 0, a is equal to 1, if lambda m minus m another m terms to m minus m, then this is m plus 1, right. So, up to this is equal to 0, and if I multiply any vector f here, we can write a 1 a to the power m f plus a 2 a m to the power minus 1 f. F is a vector, f belongs to R n, f is a vector, plus a m plus 1 f is equal to 0. Now, these coefficients are non-zero because they are comes from the characteristics equation. So, a sum of a to the power m, a to the power m minus 1 up to a to the power f is 0 means that a to the power m f with, so this with a 1, a 2, a m plus 1 non-zero. Not all of them are 0 because this is coming directly from the characteristics equation. So, this implies that a to the power m f, a to the power m minus 1 f up to f are linearly dependent. So, characteristic Cayley-Hamilton theorem says that there is a value of m at which, after which all these things will be linearly dependent. Maybe up to a to the power m minus 1 f they are not linearly dependent, they are linearly independent, and after m is equal to after we add the term a to the power m f, it will be a linearly dependent set. So, there is a particular value of m, and this can be found out. In some case it can be equal to n R n, it can some case if we have many dependent eigenvectors or repeating eigenvectors, repeating eigenvalues, it can be less than n, but there is a particular number of vectors of the Krylov subspace set which are linearly independent. So, if a to the power m minus 1 f is independent up to m is equal to n, and in some case it can be independent, it can lose its linear independence before that also. But a number of vectors can be found out here who are linearly independent if f is not an eigenvalue of eigenvector of A. So, we will find out k 1, k 2, k 3 up to k n, and then this space will be similar, because k 1 is less than k 2, I am adding one more independent vector, I am getting a higher dimensional space, and I can get up to k n, and then this space will be similar, because we will only add linearly dependent vectors with k n to get k n plus 1. So, it will be similar. So, we can have a maximum dimension of the Krylov subspace for any vector f, we can have a maximum dimension of the Krylov subspace. That means, we can update x 0 to x star, which is the right solution, on that on a finite dimensional subspace only. So, the subspace will have finite number of independent vectors, basis, a finite number of basis vectors. So, it is possible to find out that subspace, because the number is finite, and update x star from x 0 as a solution of b minus x star is equal to 0 in a single step. Now, Krylov subspace can be utilized for matrix solvers in a method, that the projection method, which uses Krylov subspace, seeks an approximate solution x m from an affine subspace x 0 plus k m. We had x 0 is the initial guess, x m, that is x 0 plus k m is the Krylov subspace now. So, x 0 plus k m such that the solution b minus a x m is perpendicular to a vector space L m, and L m and k m both are m dimensional subspace, and x 0 is the initial guess. In this case, the Krylov subspace, this can be found out using Krylov subspace methods, that is k m is k m a r 0. So, basically k m will continue all the vectors r 0, a r 0, a square r 0, a cube r 0 up to a m minus 1 r 0, which are the vectors what are to be added with x 0 if we do a number of steps of steepest descent type of method, and r 0 is the initial guess. So, Krylov subspace k m is equal to span of r 0, a r 0, a square r 0, a to the power m minus 1 r 0, etc., till we have all the vectors linearly independent vectors. After that, if we add any vector, that will be of no further use, because we have spanned the entire subspace till we have find all the linearly independent vectors here. So, this is one way of finding out k m that use the Krylov subspace of r 0, a r 0, a square r 0, and this is motivated from our initial discussion which we had in the last session, that what we are adding through a steepest descent type of algorithm is basically combination of r 0, a r 0, a square r 0, a to the power m minus 1 r 0. So, if we add a Krylov subspace vector, it will be that combination only. And now, what will be L? That will be another question, and we have to find out how we can get that L m, but k m in the entire Krylov subspace method with any initial vector x 0 will add some vector which belongs to Km of A r 0 and we will get our solution x star that solves A x star is equal to B accurately. So, our idea will be to find out these basis vectors till they are linearly independent to each other. And what L will give me, what are the coefficients that will be multiplied with all these basis vectors to get this particular vector with which will be added with x 0. That will be found out by b minus a x m at any stage is perpendicular to L m, and we will see that what is L m for these cases. So, we proceed for finding out the basis of Krylov subspace, and again I say like very simply we can find out, we can take any vector x 0, find out what is the initial guess r 0 and then x 0, what is the initial residual b minus a x 0, and then multiply with a square up to go up to m minus 1 till we see that this vector is independent with all other vectors and say that these are the basis of Krylov subspace. What is the check to find out that a new a to the power p r 0, this is linearly independent with all the previous vectors r 0, a r 0, a square r 0 up to a to the power p minus 1 r 0. What will be the check for this? Again, if I think that the vectors will be linearly independent till I find out all the eigenvalues or till I consider all the distinct p which will consider all the distinct eigenvalues of matrix A. But I then have to find out the eigenvalues of the matrix A, I have to write down the characteristics equation which will be a cumbersome exercise. The other way is that I find out whether a new vector is independent to the previous two vectors, that I take a dot product of these vectors, and if I subtract the dot products along the previous vectors from the new vector, subtract the component of the new vector along the previous vectors from the new vector. If the subtraction is 0, that means the new vector is a combination of previous vectors. If it is non-zero, then it is an independent vector, and this is what we do in a Gram-Schmidt orthogonalization. We orthogonalize it, but also when finding out a new orthogonal product, we take dot product of these orthogonal vectors are independent to each other. So, we take dot product of this vector. So, we have a vector like this, we have two other vectors, we take dot product of A with B and C, and then we subtract A minus A dot B into B by mod B minus A dot C into let us do it in little, let us do it here. So, we see that A minus A dot B, this is the component by B by mod B minus A dot, and this is again mod B to normalize it, A dot C by mod C by C by mod C, those are the unit vectors. And if this is non-zero, then A is orthogonal as well as independent, A is with B and C. If this is non-zero, then A is independent with B and C. So, this is a check whether they are non-zero or not, and this check is followed in a Gram-Schmidt process till we can find out orthogonal vectors in the Gram-Schmidt process, the vectors will be independent to each other, and we will follow a similar process to find out the independent vectors. So, what we will do, we will basically follow a Gram-Schmidt like process to find out basis of Km, and this will break all the bases of largest set is found out, k m plus 1 will fail in Gram-Schmidt. So, once all these bases are found out, then we try to find add a new vector which is k m plus 1, we will see that the Gram-Schmidt is failing, that is no new independent orthogonal vectors is being formed. So, we go to the next slide, which basically says what we discussed in form of a Carey-Hamilton theorem, that there is a positive integer nu is a function of y and a, which is called grade of y with respect to a, such that the dimension of the Krylov subspace A y is m if m is less than nu is equal to nu if m is greater than nu. So, if I add any vector after we found out the grade, after we have reached the grade of Krylov subspace of y A with respect to y, will not increase the dimension of the subspace, or we cannot find we are not adding a new independent vector to it. All the independent vectors have been found out and the maximum dimension of the Krylov subspace, the largest Krylov subspace with all independent vectors have been found out, and this directly follows, you can recheck it from what we have discussed, Carey-Hamilton theorem. The lemma 2 is that the integer in nu satisfies this particular criteria. Nu is minimum of n or the dimension of A inverse y. Either this the value of nu is n, or if A inverse y we think of finding out the Krylov subspace of A and y, or if A inverse y has a smaller dimension, it is that. So, in most of the regular matrix cases, a nu is the real coordinate dimension of the real coordinate space n. And the corollary is that if there is a solution x star, which is solution of x is equal to b, and x is equal x 0 is any initial approximation, and r 0 b minus x 0 is the corresponding residual, and the grade of y and a, nu is the grade of nu y a, then, or nu is the grade of not nu y a, I should write nu is the grade of nu r 0 a, instead of y a you can take nu is the grade of nu r 0 a, because now we are finding out Krylov subspace for a r 0. So, nu r 0 a, then the final solution x star must be a member of affine space, which is found out by x 0 plus k nu, nu is the grade of Krylov subspace with respect to r 0, k nu a r 0. The sequence of solution x nu is equal to x 0 plus k n a r 0. So, I start with one particular basis of Krylov subspace, we update x 1, and we add all the basis of we add another particular basis of Krylov subspace, we update it, and we add all this and we find out that the sequence x 0 plus all the vectors of Krylov subspace, this solution will converge to x 0 and the residual R n will converge to R 0. The second one is actually very easy to prove, that we can write R n is equal to R 0 plus alpha R 0 plus, if I just write A x n is equal to x 0 plus b and b minus A x n I do it, then I alpha 1 R 0, alpha 2 A R 0 plus alpha 3 A alpha 3 A square R 0, and it goes up to alpha something. So, alpha 1 alpha 2 a to the power nu R 0. So, A has a power 0, A has a power nu. So, this will be alpha nu plus 1 r 0, and then if I add any vector theta a to the power nu plus 1 r 0, then this particular set is linearly independent. If I add anything on that, this is a vector which is dependent on this. This is a linearly, this is a spanning set. If I add any further vector, this is something on the spanning set only, and with right choice of theta I can cancel this and say that R n will be 0, because I am adding a non-independent dependent vector here. So, I can have non-zero coefficients of all these all the non, or at least few non-zero coefficients of these vectors, and the solution can be 0, still they are non-zero. So, R n will converge to 0. K m is the subspace of all vectors in R n, which can be expressed as P a is R 0, and P a is a polynomial if and P a is a polynomial whose degree cannot be more than m minus 1. So, K m will be a polynomial of A into R 0, polynomial of the vector, of the matrix into R 0, and this will not have a degree more than m minus 1. So, this is how will be K m. K m is basically combination of R 0, A R 0, A square R 0 up to m minus 1 R 0. And the next question is that how will be L m, because once we find out L m and put the criteria that b minus x m is perpendicular to L m, then we can find out which coefficients will multiplied with all the basis vectors of K m to update my solution x 0 to x m. So, the question also becomes how is L m, and now there are two different versions of Krylov subspace methods. They arise from different choice of L m. For any Krylov subspace method, K m is fixed, K m is R 0, A R 0, a space spanned by R 0, A R 0, A square R 0, A to the power m minus 1 R 0 till m minus, they are independent till we reach the grade of the matrix A with respect to R 0. How will be L m? So, there are two different versions of Krylov subspace method from which are broadly from the choices of L m. Also there is something called a precondition, the way they are preconditioned. We will discuss about the preconditioning methods at the end of this syllabus. Let us say that there are two particular choice of L m. For L m is equal to K m, L is equal to K, then we call it an orthogonal projection, or it is called a full orthogonal method when L m is equal to K m. And if L m is equal to A K m, it is not an orthogonal method, or rather it is an oblique method. So, this becomes an oblique method, and one oblique method we have found out in one dimensional projection, which is minimum residual method. So, the similar methods like this is generalized minimum residual method, GMRES, that use L m is equal to A K m, and this is an oblique projection method. So, one class of this is full orthogonal method or FOM, where L m and K m are same. The other class of method which are oblique projection methods, L m and K m are not same, and we will use L m is equal to A K m. For a transpose based method or another variant of Krylov subspace method is also used, where L m may not be equal to K m, especially for non-symmetric matrices, and we will use in the later part of this when we will do Beilangs's algorithm, where we will find that L m is some type of a combination of a Krylov space of A as well as combination of a Krylov space of K transpose A transpose, which will come in the maybe after 1 or 2 weeks when we will discuss about Beilangs's algorithm or biconjugate gradient. So, this can also be an oblique method for non-symmetric matrices, but in general there are two methods, orthogonal method and oblique method. BiCG can be orthogonal for symmetric matrices, will be oblique for non-symmetric matrices, but for a general matrix, if you already know, there is one full orthogonal method where Lm is equal to Km, and there is another method which is non-orthogonal method, GMRES or minimum residual methods are member of that class where Lm is equal to Akm, and using this we also get certain variants in these two large class of methods. So, we quickly look that how to find out the basis vectors of Km, and this is known as Arnoldi's method. What we do is discuss here is called Arnoldi modifier Gram-Schmidt, which is finding out basis vectors of a Krylov subspace. So, I have a Krylov subspace say V1, A V1, A square V1, A to the power m minus 1 up to A to the power m minus 1 V1, and I need to find out the basis of this subspace. Basis means at when I add, it can go up to A to the power nu minus 1 V1, but when I add A to the power nu V1, this is not required because this becomes a dependent vector. So, I have to find out till when these vectors are independent, and I said like we will use a Gram-Schmidt type of algorithm. The other advantage of a Gram-Schmidt algorithm is that at every iteration we get orthogonal unit vectors or orthonormal vectors. So, when we will use Arnoldi's method, this method will use a Gram-Schmidt algorithm, and it will go till we find out orthonormal basis of the Krylov subspace. So, this is one basis of the Krylov subspace, but we will not find this particular basis. We will find an orthonormal basis V1 and AV1 may not be perpendicular to each other, and as well as V1 and AV1 may have non-zero modulus, but when we will find an orthonormal basis, the vectors will be perpendicular to each other. So, we will find out the unit vector used from V1 by mod V1, and then we will take AV1 and take its dot product with V1 by mod V1, subtract it from AV1. What will be remaining with us? We will normalize that and we will say that this is the second orthonormal vector. We will go up to A minus 1, we can go up to A nu minus 1, and once we have arrived here, that for the next vector, when we take its dot product with all the previous vectors and subtract it from here, we will be not remaining with anything. So, it will be a 0 vector, and we will say that the process should stop here, because we have found out all the maximum all the basis vectors for the largest Krylov subspace, where it goes up to the grade of the matrix with respect to the given vector. So, choose a vector V1 of norm 1 or get any V1 and orthonormalize it to get its norm 1. So, first vector V1 should be norm 1, then compute W is equal to AVJ, which is the next vector in the Krylov subspace. Take dot product of W with V and subtract it from W. So, we get a vector which is perpendicular, the W1 will be perpendicular to V1, and then find out its modulus divided by the modulus. If the modulus is 0, then all the independent vectors have or orthogonal vectors have been found out. There cannot be no further orthogonal vector, and where it breaks down with the modulus of W is equal to 0, that particular value we will call, we reach the grade of the Krylov subspace, and these are the maximum number of independent vectors here. But if m is less than that, then it will continue till m, maybe after we went up to m is equal to 15, but the grade is 20. So, you did not reach the grade, we have stopped there. So, you have to find out maximum, this will give us maximum m basis vectors of Km. It might break before that, and we will get less than m basis vectors, because the dimension is less than m in that case. And this procedure does not stop before mth step. V1, V2, Vm will form an orthonormal basis of Krylov subspace. So, it will be also of better help, because the vectors that I am getting out of it are orthonormal vectors, and it is always easy to deal with orthonormal vectors, because they are unit vectors in each perpendicular direction. So, given any vector, I can take dot product with respect to orthonormal vectors and find out what are the coefficients in each direction. So, and the method that we discussed is Arnoldi modified Gram-Schmidt. At each step, this algorithm multiplies Arnoldi vector with Arnoldi vector V j with A and then orthonormalizes the resulting vector W j against the previous V j's by a standard Gram-Schmidt type of procedure. So, I can again show that I take a vector V 1, the same algorithm we discussed here. We take its product, first one is V 1, the next vector in the subspace is A V, we take its dot product with V 1, subtract it from W, the magnitude we find out. If the magnitude is 0, then this is the W is dependent on the previous V's. If it is non-zero, then we divide it by, the W by this and get another orthonormal vector and find the next vector which is A V into A, that means this will give me A square V, the next power of this. So, this method gives results into V, which will be the basis of the subspace, which will give a base set of vectors will be the basis V of K M. V will contain. So, V the vector the matrix capital V will have all the vectors V 1, V 2 up to V m. We will have, and all these are basis vectors of K m. So, we will find all the basis vectors of K m. And what we get as H j is an interesting vector matrix. This will continue have like the upper triangular matrix we formed using Gram-Schmidt, the R matrix that we are finding using Gram-Schmidt. Along with that, there will be one row which is also non-zero row. So, H is of a Heisenberg form, where it is a upper triangular matrix with one non-zero row, and this is called a Heisenberg matrix H j. So, denoted by the matrix V m, which is an n into m matrix, because there are each vector in V m is in R n and there are m vectors in V m with column vectors V 1, V 2, V m. By H bar m, the m plus 1 into m Heisenberg matrix whose non-zero entries are defined by Arnoldi modified Gram-Schmidt, and we define by H m. So, this is my H bar m, which is an Heisenberg matrix, and H m are upper triangular matrix, another Heisenberg matrix, which is obtained by deleting the last row of H bar m. So, I have H bar m, which is basically upper triangular matrix with another row here. Now, I delete the last row, there is one element here. I delete the last row, I get a matrix which is simply an upper triangular matrix with a Heisenberg diagonal, and we denote this by H m. So, then there is a, if you go back to the algorithm and try to explore it, there is a relation that A V m is equal to V m H m, this H m into W m E m transpose. E m is basically an unit vector of which gives me the mth I will say the mth basis, unit vector which is mth basis part of. So, E m is equal to 0 0 0 0 1 something and then 0 and then 1 1 and 0 0, and this 1 is at mth position. If I look into the algorithm, we can very easily find out that this relationship holds, as well as this relationship also can be proved that V transpose A V m, V is the collection of the all basis vectors of Krylov subspace, is this Heisenberg matrix H m. Or we can write A V m is equal to V m multiplied by H m, which is a Heisenberg matrix with a with the last row being deleted, plus W m E m transpose. This is a important relation which will be utilized when we will deal with the basis vectors of Krylov subspace to design the algorithm for matrix solution like full orthogonal method. We already, when we will find out the basis vectors and then see that how they can be projected with respect to how the residual can be projected with respect to an LM which you have taken, and we can simplify it and get the coefficients which will be multiplied with the with V1, V2, Vm to get the final solution. These relationships will be utilized. So, in the subsequent discussions we will utilize these relationships to design a matrix solver using the basis vectors of Krylov subspace which we are getting through Arnoldi modified Gramscian method. Thank you.